So I want you to imagine that you have to build this really complex multi-story house, but there is a massive catch to the whole thing.
Oh, boy.
Yeah. Your construction site is, well, it's 140 million miles away.
Right.
And the air there is entirely toxic. The dirt is irradiated. And you have to somehow bring the entire lumber yard, the concrete mixers, the power plant, everything with you on a single truck ride.
Which is just, I mean, a logistical nightmare on its own.
Exactly. But on top of that, your construction workers, they only understand instructions that you gave them 20 minutes ago.
Yeah, right. The delay.
And to make matters even worse, the environment outside this house is actively trying to destroy your materials day and night. So how do you even begin to solve that? Well, today, you are joining us for our next deep dive into complex engineering, and we're looking exclusively at the exact engineering blueprint that is trying to solve this scenario. We're looking at the Tesla and SpaceX roadmap for multiplanetary preparation, specifically, the synergies between Starship, AI-enabled autonomy, closed-loop systems, and in-situ resource utilization. All of this pointing towards self-sustaining Mars bases.
Yeah. Wow. It is a massive, massive topic. And right off the bat, I think we need to ground this conversation for everyone listening.
Definitely.
Because when you hear phrases like Mars base or, humanoid robots off-world, your brain instantly just goes straight to science fiction.
Oh, 100%. It sounds like a movie.
Right. But what we are talking about today, it isn't magic. It is just insanely hard engineering. And the secret sauce here, the thing that actually shifts this from a movie script into reality, is vertical integration and just this relentless iteration.
Exactly. We are looking at this strictly through the lens of thermodynamics, manufacturing economics, and software architecture.
The boring stuff that actually makes the cool stuff happen.
Exactly. To solve that ridiculous house-building scenario, you have to completely rethink the fundamental economics of the truck, the intelligence of your workers, and the resilience of your power plant.
Right, the three pillars.
Yeah, and if any one of those three pillars fails, the whole endeavor just collapses. So, let's start with the truck. Because to even worry about building a habitat on Mars, you first have to get millions of tons of cargo out of Earth's gravity well, and you have to do it economically.
Economically being the operative word there.
Right. And we have some incredible data from a recent Archive paper regarding launch costs and what the aerospace industry calls the learning rate.
Yeah, the math on this is just absolutely fascinating, especially if you step back and look at the historical data. Because traditionally, aerospace has been completely stagnant when it comes to cost curves.
Yeah, for decades.
Right. But SpaceX has demonstrated this historical 20% learning rate. And in manufacturing economics, this is tied to Wright's law.
Which is, just to clarify for everyone, that's basically about scaling, right?
Yeah, exactly. It essentially states that for every cumulative doubling of mass produced, or in this specific context, mass launched into orbit, the cost drops by a predictable, fixed percentage.
Right.
And the data from the sources shows they've hit that 20% mark consistently. From the early days of Falcon 1, scaling up to Falcon 9,
Yeah.
and then Falcon Heavy.
Wait, hold on. I want to push back on the scale of this for a second, because the numbers in this paper are just staggering.
Oh, they really are.
Like, the projections suggest that if Starship achieves 100 times reuse for its components, launch costs could drop to under $15 per kilogram to low Earth orbit.
Phew.
Yeah.
$15 a kilogram. Just to give you some context, the space shuttle was something like, what, $54,000 a kilogram?
Something absurd like that, yeah.
And even the Falcon 9, which completely revolutionized the modern launch industry, is sitting around $2,500 a kilogram.
Right. So dropping to $15, it literally sounds like a typo in the spreadsheet. How is a 99.9% reduction physically possible?
It sounds impossible until you look at the physics of full reusability versus partial reusability or expendable rockets.
Okay, break that down.
So the space shuttle was wildly expensive because it wasn't truly reusable in an airline sense. It was refurbishable.
Right. There's a huge difference there.
A massive difference. They had to strip the engines down completely, inspect every single blade in the turbo pumps, and basically maintain a standing army of thousands of highly specialized engineers for months between every single launch.
Which eats up all your cost savings.
Exactly. Starship introduces a completely different paradigm. It is designed from the metallurgy up for airline-like operations.
Meaning you just gas it up and go.
Literally. You pump in liquid oxygen and liquid methane, you fly, you land, you inspect it real quick, and you fly again. The vehicle cost is amortized over hundreds of flights. So that leaves the propellant as your primary marginal cost.
Okay, but let's talk about the cascade effect of that. Because dropping the mass penalty doesn't just make it cheaper to send the same things, it fundamentally changes what you can send, right?
Precisely. It changes the entire physics of off-world engineering.
How so?
Well, right now, if you are building a satellite or a rover, you treat every gram like it's made of solid gold. You engineer a water pump to be the weight of a feather.
Oh, I see. Because it's so expensive to lift.
Right. You use exotic materials like beryllium or titanium. You shave off every fraction of an ounce, which means you spend, $10 million in R&D and manufacturing just for a water pump.
A pump that might just break because it's so delicate anyway.
Exactly.
Right, because at $54,000 a kilogram, you simply can't afford to send a heavy pump.
Exactly. But here is why this matters so much for Mars. At $15 a kilogram, you don't have to engineer that bespoke featherweight pump anymore.
You can just go to the hardware store.
Literally. You can go buy a heavy, durable, industrial cast iron water pump and just strap it to the rocket. The mass penalty is practically gone.
That is wild to think about.
You can send heavy industrial energy hubs. You can send raw, brute force robotics. You can send thick, heavy radiation shielding. You replace expensive, fragile complexity with cheap, heavy durability.
Which completely accelerates your R&D timeline. You aren't spending 5 years designing a lighter gear. You're spending 5 minutes loading a heavier, proven gear onto the ship.
Exactly. It's a total paradigm shift.
And that ties directly into how they're actually building this massive truck, right? The speed at which they're developing Starship is heavily tied to this concept of vertical integration.
Oh, absolutely.
Because unlike traditional aerospace, where you might have, one contractor building the fuel valves in Ohio, another writing the avionics software in California, and another building the hull in Europe.
Yeah, the classic cost-plus nightmare.
Right. SpaceX is doing basically everything under one roof.
The walk down the hall feedback advantage. This is critical to understand because it bypasses that whole traditional contracting nightmare.
Yeah.
In a standard setup, if the software team realizes, hey, we need a sensor placed 2 inches to the left to get a better reading on a landing burn, they have to draft a proposal.
Ugh, the paperwork.
Right. That proposal goes to a review board, then it's sent to the subcontractor who quotes a price and a 6-month timeline to just redesign a simple bracket.
And by that time, the entire vehicle design might have changed anyway.
Exactly. But with vertical integration, if that same software team needs the sensor moved, they literally walk down the hall, go to the manufacturing floor, talk directly to the machinists, and by the end of the shift, the next iteration of the rocket has the sensor moved.
It's incredible, and you see this perfectly illustrated in the Starship heat shield tiles.
Oh man, the tiles.
Atmospheric reentry is arguably one of the most brutal environments in the known universe. I mean, you are taking a vehicle the size of a skyscraper, hitting the Earth's atmosphere at orbital velocities of around Mach 25.
Which is just, mind-boggling speed.
Yeah. And you're compressing the air in front of the ship so violently that it generates a plasma shockwave reaching over 1,400 degrees Celsius.
And historically, dealing with that plasma was the ultimate bottleneck of reusability.
Right.
If we look back at the space shuttle again, the heat shield was made of these incredibly fragile, unique silica tiles.
Right.
There were thousands of them. And almost every single one was a custom shape fitted to a specific curve of the shuttle's belly.
So if one breaks...
If one cracked, you had to manufacture that exact specific shape again.
Yeah.
It required thousands of hours of manual visual inspection between flights.
But with Starship, they are trying to achieve that airline-like cadence. You can't have an army of technicians inspecting tiles for 3 months if you want to fly again tomorrow.
Oh, not at all.
So they had to design a heat shield that isn't just robust, but essentially self-healing, or at least so rapidly replaceable and uniform that it doesn't throttle the launch cadence.
Which is why they went with uniform hexagonal tiles.
Yep.
By making them hexagonal, there are no straight continuous lines across the hull for the superheated plasma to channel down and act like a blowtorch.
Oh, that makes so much sense.
Yeah. And because they are mostly uniform in shape, they can be mass-produced cheaply and slapped on quickly. But getting the ceramic composition and the mechanical attachment right so they don't just rattle off during the intense acoustic vibrations of launch has been a brutal engineering challenge.
But the way they're solving it is what's crazy. I mean, the rapid prototyping they are doing with these tiles, testing them on live flight tests, actively watching them shatter or melt or fall off during reentry, tweaking the ceramic composition or the backing pins and throwing them right back onto the next test vehicle that is already sitting on the pad. I mean, holy shit, that iteration loop is brilliant.
Huh. It really is. They are utilizing the entire flight program as a massive, destructive testing lab.
Which is wild.
They don't expect perfection on the first try. They expect failures. But they instrument the failures so densely that the telemetry data feeds directly into the next build, which is already physically on the assembly line.
Wow.
It is hardware development moving at the speed of software agile development.
Right.
It's an entirely different philosophy of engineering.
And we should anchor this for a second. This is the scenario that engineering points toward.
Right.
We're looking the math, the physics, and the stated roadmap in these white papers. If they achieve this high-cadence, low-cost transport, the mass problem is essentially solved. You can drop thousands of tons of cargo habitats, solar arrays, rovers, batteries straight onto the Martian surface.
But having a pile of cargo on the surface immediately introduces the next critical bottleneck.
Right, because let's say you have a fleet of cheap rockets and they successfully land all this hardware in the Martian dirt. Now what? You have a pile of inert metal. You need to assemble it into a functioning base before humans arrive. So the logical first thought for most people is, well, we'll just have operators on Earth joystick some robots to unpack the cargo and weld the base together.
And that is where the physics of the solar system completely shut you down. Human teleoperation from Earth is impossible because of the speed of light.
It's just too far away.
Way too far. Depending on the orbital alignment of Earth and Mars, communication takes anywhere from 4 to 24 minutes each way.
Think about what that actually means for a second. Let's say you are sitting in a control room in Texas, looking at a video feed from a robot on Mars.
Okay.
You see the robot reach out to pick up a steel beam, but its foot slips on some loose sand and starts tipping over. You instantly jam the joystick to correct its balance. But that video feed you just watched, that happened 20 minutes ago.
Right. It's already tipped over.
Exactly.
Right.
And your command to fix the balance, that's going to take another 20 minutes to reach the robot. So 40 minutes have passed, the robot has been lying face down in the dirt for over half an hour, and your multi-million-dollar construction project is just halted.
This is exactly what forces the necessity of AI autonomy. You cannot rely on a permission slip from Earth. The intelligence has to be local.
It has to be on the ground.
Yes, the AI has to make decisions at the edge, in real time, to react to an entirely unstructured environment.
Now, if you're listening to this and thinking, sure, an AI can navigate a factory floor, but building a base on an alien planet is completely different, you have to look at the synergy between Tesla's Earthbound AI and SpaceX's off-world goals, because it's the exact same underlying architecture.
It really is. The AI running full self-driving on Earth is fundamentally about navigating chaotic, unstructured environments using pure vision.
Just cameras.
Just cameras. A Tesla vehicle has to look at a complicated intersection, identify pedestrians acting unpredictably, interpret weather conditions, read temporary construction signs, and make safe trajectory decisions in milliseconds.
Right.
When you take that exact same visual neural net and put it into a rover or a humanoid robot on Mars, the physics of the problem are identical.
It's just a different training environment. Instead of looking out for stop signs, traffic cones, and jaywalkers, the neural net is looking out for loose regolith, steep impact craters, and incoming dust storms.
Exactly. Same math, different visuals.
And we are seeing this exact technology being embodied in Optimus, Tesla's bipedal humanoid robot.
Which makes perfect sense when you think about the form factor required for Mars. You aren't going to have the luxury of sending a highly specialized robot for every single niche task.
Right, you can't have a whole fleet of specialists.
No, you can't send one robot just for turning a specific wrench, another robot just for carrying solar panels, and another robot just for sweeping dust off the airlocks. You need to send a general-purpose form factor that can adapt to whatever the environment throws at it using tools designed for human hands.
But here is the massive problem. How do you train a robot to work on Mars when it is physically stuck on Earth?
Yeah, that's the million-dollar question.
You can't exactly take Optimus to the local park and simulate a 0.38 gravity environment with a toxic carbon dioxide atmosphere and a temperature of minus 60 degrees.
No, you definitely cannot. And this is where digital twins and massive simulation come into play. And this is where Dojo Tesla's custom supercomputer architecture is absolutely critical.
Tell me about that.
So engineers build hyper-realistic, high-fidelity physics simulations of the Martian surface. We weren't just talking about making it look like Mars in a video game.
Right, it's not just a graphics engine.
Exactly. They simulate the exact shear strength and friction of the Martian dirt. They simulate the exact mass and torque of the tools in Martian gravity. They simulate the harsh, unscattered lighting conditions that can blind cameras. Then, they drop millions of virtual Optimus robots into this simulation to practice building habitats.
A year of Mars ops simulated in a week. Wow.
It is staggering compute power. The AI is learning how to balance its bipedal frame, how to walk over uneven terrain, how to handle heavy materials without tipping over in reduced gravity, all entirely in the digital realm.
That's wild.
By the time the actual physical hardware boots up on the real Mars, the neural net in its brain has already experienced centuries of trial and error.
It's funny to think about what Optimus actually represents in this context. On Earth, people joke about having an AI robot to do their laundry or grab their groceries. Optimus on Mars is basically the ultimate burrito ordering intern, except it's actually building the habitat.
But right, the stakes are just slightly higher than getting your lunch order right.
Slightly. But the tasks they are going to be doing are critical to survival, and one of the most important elements of this blueprint is In-Situ Resource Utilization, or ISRU.
Yes. ISRU is everything.
Because you cannot bring all the oxygen, water, and rocket fuel you will ever need for a sustained presence from Earth. The launch mass would be astronomical. You have to manufacture it locally.
Yelena, you read the ArtCiv paper. How insane is the ISRU part?
Oh man, it's completely mind-bending. It takes ISRU from a delicate, tiny science experiment and scales it up to a massive industrial pipeline. Like, we saw a proof of concept with the AMOXA instrument on the Perseverance rover, which successfully extracted a tiny bit of oxygen from the Martian CO₂ atmosphere. But AMOXA was the size of a toaster. The roadmap calls for factories the size of football fields.
Yeah, huge leap.
And AI is the only way you manage that transition without human crews on the ground.
Exactly. Let's really break down the chemistry and the mechanics of what these autonomous systems will actually be doing, because this is where the engineering gets incredibly dense.
Go for it.
So the Martian atmosphere is roughly 95% carbon dioxide, but it is also incredibly thin, about 1% the density of Earth's atmosphere at sea level.
Almost a vacuum.
Basically. So to even begin the chemical process, you have to run massive compressor pumps to suck in this near-vacuum atmosphere and pressurize it.
And once you have the pressurized CO₂, you have to run it through the Sabatier process. With the right energy input and a catalyst like ruthenium or nickel, you combine that carbon dioxide with hydrogen at temperatures around 400 degrees Celsius. This chemical reaction produces methane, which is your rocket fuel, and water. You then run electrolysis on the water to split it into hydrogen, which you feed back into the Sabatier reactor, and oxygen, which you store for breathing and for oxidizing the rocket fuel.
But notice the missing ingredient there. You need an initial source of hydrogen, which means before you can make fuel, you have to mine subsurface water ice.
And mining ice autonomously is a literal nightmare.
It is. The terrain is entirely unpredictable. The ice isn't pure. It's mixed with highly abrasive regolith and perchlorates.
So it's like drilling through frozen concrete.
Worse. If you just program a drill to push down at a constant speed, the bit will inevitably hit a buried rock, bind up, and snap.
Yeah.
An AI has to be monitoring the telemetry in milliseconds.
It has to feel the drill.
Exactly. It has to instantly recognize a micro spike in the torque of the drill motor, realize it's hitting a rock, back the drill out, adjust its angle, and try again, completely autonomously.
And then there's the physical construction of the base itself. You have to process the regolith. You can't just pile dirt on top of a habitat for radiation shielding. It'll just collapse.
Right, it's too loose.
You have to sinter it. Sintering means using microwaves or high-powered lasers to literally melt the Martian dirt into solid, interlocking, 3D printable construction materials.
Just melting the ground.
Yeah, and doing all of this, mining ice, running Sabatier reactors, lasering dirt into bricks, assembling the modules, it requires a symphony of moving parts.
Which brings up the concept of swarm coordination, because you don't just have one master robot doing all of this sequentially. You have a swarm of heterogeneous nodes.
It's like an ant colony, right?
That's a perfect analogy. An ant colony doesn't have a central command center telling every single ant where to step. They operate on local rules that create complex global behavior. On Mars, you have orbiters in the sky taking high-resolution thermal and topological maps. They beam that data down to the landers, which act as local compute hubs. Those landers coordinate with rovers and a fleet of Optimus bots on the ground.
And they communicate via local mesh networks. It's an entirely decentralized system.
Yep.
Like if one Optimus bot is walking across a plane and encounters a steep drop-off or a patch of soft sand that wasn't on the orbital map, it instantly updates the local mesh. The entire swarm now knows that hazard exists and routes around it dynamically.
And they use that same network to execute complex construction sequencing.
Exactly. One robot holds the steel beam in place, another robot welds the seam, a third robot inspects the weld with computer vision, all safely, all autonomously, without ever waiting for Earth's permission.
Yeah, the coordination is brilliant.
Okay, so you have these autonomous swarms building a base. You have drills mining ice, compressors sucking in the atmosphere, and lasers melting dirt. But all of that, especially the Sabatier process, requires an unbelievable amount of electricity.
Oh, absolutely massive amounts.
Right. So what happens to your robot swarm and your fuel production when a Martian dust storm blots out the sun for 3 months? How do you keep the lights on when the environment actively wants to kill your power grid?
That is the ultimate bottleneck, energy. If the power dies, the mission dies. And here's where we look at how Tesla energy technology, specifically the integration of solar, Megapack, and Powerwall architectures, is adapted for a closed-loop, off-world environment.
The power requirements are simply astronomical. I mean, we mentioned the ISRU plant, but once humans actually arrive, you also have life support systems.
Yeah, keeping people alive is expensive energy-wise.
Very. You need continuous air revitalization, maintaining the exact atmospheric pressure and the perfect oxygen-nitrogen mix. You need aggressive thermal regulation because Mars is a frozen desert.
Crazy.
The temperature can plummet to minus 100 degrees Celsius at night. If you lose power for even a few hours, the habitat freezes, the water pipes burst, the algae in the food systems die, and the crew perishes.
So absolute, uncompromising reliability is paramount. But the stressors on Mars are almost comical in their severity. You have massive, rapid temperature swings between day and night.
Right.
That thermal cycling causes material to expand and contract continuously, which fatigues metal, degrades battery chemistry, and literally cracks the microscopic solder joints on circuit boards. And then you have micrometeorite impacts.
And the dust. We have to talk about the dust.
The dust is arguably the absolute worst part of the entire Martian environment.
Hey, it really is. I mean, you are trying to operate delicate, highly efficient solar panels and battery storage tech during global Martian dust storms that can literally block out the sun for months at a time. It's absurd.
It really is.
And it's not like beach sand. The dust is incredibly fine, like talcum powder or smoke. And because of the dry, irradiated environment, it is electrostatically charged.
Right. It clings to absolutely everything. It coats the solar arrays, plummeting your power generation to near zero exactly when you need it most to run the life support heaters through the darkness.
Which is why the energy hubs cannot rely on a single point of failure, and why they must be deeply integrated with the AI we were just talking about. The system has to forecast power generation drops.
Predicted AI.
Exactly. If a weather orbiter detects a regional dust storm developing in the northern hemisphere and heading toward the base, the AI in the energy hub has to proactively triage the power grid. It might pause the energy-hungry ISRU fuel production to ensure the megapacks remain fully charged, hoarding every joule of electricity to sustain the life support thermal loops through the storm.
But the AI brains running these energy hubs, the physical silicon chips themselves, they face an invisible threat that is even more dangerous than the dust or the cold: galactic cosmic rays.
Oh man, the radiation data from the sources is incredibly sobering. Here on Earth, our thick atmosphere and our strong magnetic field protect our data centers and our brains from the worst of space weather.
We're so lucky.
We are. Mars doesn't have a global magnetic field, and its atmosphere is practically non-existent. The surface is constantly bombarded by high-energy protons and heavy ions from deep space.
To understand how devastating this is to hardware, researchers actually tested Google Tensor Processing Units, or TPUs, by blasting them in 67 MeV, that's mega electron volt proton beams.
Wow.
They were trying to simulate this harsh, deep space radiation environment to see exactly how and when the AI hardware would fail. They were specifically looking for two things: total ionizing dose, or TID, and single event effects.
Let's explain those, because understanding the mechanism of failure is critical. Total ionizing dose is basically the gradual accumulation of radiation damage in the silicon over time. It's almost like rust.
Good analogy.
The environment on Mars exposes unshielded hardware to about 150 rads per year. As these particles pass through the silicon dioxide layers of the transistors, they create trapped electrical charges. Over a 5-year mission, the silicon physically degrades.
Right.
And the tests showed that while the core logic held up surprisingly well, the high bandwidth memory, the HBM, which is crucial for running large neural nets, was highly sensitive, showing severe irregularities after just 2,000 rads.
But while TID is a slow death, the single event effects are the immediate catastrophic nightmare.
Right. What exactly is a single event effect?
Well, it happens when a single high-energy particle strikes a sensitive node in a microchip and deposits enough energy to literally flip a bit. A 0 becomes a 1, or a 1 becomes a 0.
And if that bit happens to be part of a JPEG image, maybe you just get a weird colored pixel. But if that bit is part of the code controlling the oxygen mixture valves in the life support system, a single flipped bit could crash the entire habitat.
Exactly. This forces engineers to fundamentally alter the hardware and software architecture. They have to use radiation-hardened chip designs, which physically separate the transistors to make it harder for a single particle to hit multiple nodes.
Spacing them out.
Right. But more importantly, they implement massive software-level redundancy, like error-correcting codes, or ECC. The AI running the Mars base has to be deeply paranoid. It has to constantly check its own math, running identical calculations through 3 different processors simultaneously, and using a voting system to ensure radiation hasn't corrupted its decision-making.
And when you combine this paranoid energy and data management with the life support systems, you get into the realm of bioregenerative closed loops.
Right. The biology?
The sources mention the European Space Agency's Melissa concept. This isn't just about managing batteries and thermal loads, it's about managing an entire ecology.
You are creating a synthetic biosphere from scratch. You have crew waste, which has to be broken down by specific nitrifying bacteria in a bioreactor.
Yeah.
Those bacteria produce nutrients and CO2, which feed an algae photobioreactor. The algae produce oxygen and edible biomass for the crew, who then produce waste, starting the loop over again. It is an incredibly delicate, interlocking biological balance.
And it is hypersensitive to the energy grid. If the power drops and the temperature falls a few degrees, the nitrifying bacteria slow down their metabolism. If they slow down, the algae don't get enough nutrients. If the algae die, the oxygen levels in the habitat start dropping.
And human operators cannot monitor all those thousands of biochemical variables fast enough to prevent a cascade failure. The AI has to monitor the chemical composition of the water loop in real time, predicting microbial growth rates and instantly adjusting the thermal and power loads across the base to maintain absolute homeostasis.
So it's doing everything.
It's an energy hub, a data center, and an automated greenhouse, all wrapped into one, surviving on a frozen, irradiated desert.
Which brings us to the bigger picture. When you step back and look at these 3 pillars, Starship providing the sheer brute force mass transport capability to bypass the cost penalty, Tesla AI and Dojo providing the localized, highly trained autonomous robotic workforce, and the energy hubs providing the robust radiation-hardened heartbeat of the colony, it all weaves together.
It does.
It is not a disparate collection of tech projects. It is a single, cohesive roadmap for a multiplanetary civilization.
It really is awe-inspiring when you view it from a high-level systems engineering perspective. We aren't just talking about planting a flag, taking some photos, and leaving footprints. The engineering we just walked through is meticulously targeting the exact physical and economic bottlenecks of sustained, permanent habitation.
We're still early, but the roadmap is wild. To think that right now, as you are listening to this, heat shield tiles are being baked in ovens and tested in plasma tunnels, and neural nets are navigating simulated Martian regolith in a supercomputer, well, it's happening.
The foundation is being poured.
And speaking of big engineering visions, we've been looking at a bunch of other white papers lately, and there's one coming up soon called The Convergence Lattice by Martin B. Joseph.
Martin B. Joseph. Come to think of it, Martin aligns more with Musk's thesis, actually.
Exactly. We're going to dive deep into that one very soon, so stay tuned.
It's going to be a good one.
Phew, that was a lot. The engineering roadmap for becoming multiplanetary is wild.
If this shifted how you think about self-sustaining Mars bases, drop your thoughts below.
Huge thanks for riding along. Go check out the sources we linked, especially Solving the Money Problems channel for more on this stuff. We'll see you in the next episode. Until then, stay curious and take care.